Hello, everyone. Welcome to today's CHAMP talk. I'm happy to introduce Sankhaneel Bisui from Tulane, yes, who will tell us about stable Harbourne, not Hartshorne, Huneke containment, and bounds on Waldschmidt constant. Sankhaneel.
So, hi everyone. First of all, I would like to thank the organizers, Eloisa and Sean, for organizing this beautiful online seminar and giving me the opportunity to talk about my work. And as Sean already said, it's about stable Harbourne Huneke containment and bounds on Waldschmidt constant. And so let's see some motivational background that that inspired us to study this containment and most of all the Waldschmidt constant. So for a polynomial in one variable, we can determine the polynomial completely by its zeros. So let's talk about something general scenario. Suppose we are given S number of points inside the affine line A and C. Now we want to determine a polynomial of degree D. Suppose we call it fx to be a0 plus a1x plus up to a dxt. And we want the D degree to satisfy the condition that D plus 1 is equal to sum of mi. I'm going to introduce the mi's in a bit. So this polynomial will be vanishing on the set X with multiplicity m1 up to ms respectively. And this polynomial can be uniquely determined by the conditions, by the vanishing conditions on the derivatives, meaning the partial of the f up to the power mi minus 1 for each point xi has to be 0. Now, this phenomenon, you might have seen it, and it is also known as the Hermit Interpolation. Let's see what happens when we talk about something in a general setup, meaning in a scenario when we have a polynomial with several variables, or we have points in multidimensional projective space. So throughout the talk, I will be assuming my field to be complex numbers if it is not specified, and we'll be writing PNC or PN alternatively. Now I'm gonna take M1 up to MS to be finitely many natural numbers and X to be a set of points P1 up to PS inside the projective space. Now polynomial interpolation says, given the set of points inside the projective space and positive numbers M1 up to MS, we want to study the set which contains all the homogeneous polynomials that will vanish on the set X with multiplicity M1 up to MS. And the set sits inside the coordinate ring or the polynomial ring with complex coefficients. Now, with a easy observation, we can see this set LXMI is an algebraic object, and it is going to connect geometric properties of X with some algebraic structure. What I am interested to see what is the minimal D inside N, meaning minimal D, such that the set has a polynomial of degree D. I am also interested in somehow to see, given a fixed D, what would be the dimension of the D degree polynomials inside that set. Now, in a general scenario, it is really difficult to study when M1 and the multiplicities are different. So we will be studying the scenario when we have equimultiplicity, meaning each M1 up to MS are same, let's call it M. So the question again becomes, what is the minimal degree D such that the set has an polynomial of degree D? Now, a small note, just a reminder that all hypersurfaces in a projective space are defined by homogeneous polynomials. In 1965, Nagata raised this question. If you take a finitely many points, P1 up to PS inside the projective plane, what is the minimal degree alpha tx of a hypersurface that will be passing through those points with multiplicity at least t? So in some sense, studying the question is same as studying the question raised by Nagata. So our goal is to study the lower bound, because the study of exact degree alpha tx is really difficult. Which is more desirable is to study the lower bound of this alpha tx. Now, Nagata gave an conjectural answer in terms of the lower bound, and it states as, if you take X to be a general set of S points inside the projective plane, then the ratio of the alpha Tx over T is at least square root of S. Later on, Junoskis also gave an conjectural answer to the same question, and the answer is given by the lower bound as follows. The ratio alpha Tx over T is at least alpha x plus n minus 1 over n for all T, and alpha x meaning the least degree of the hypersurface that will pass through those points one time. And de Mailly generalized that lower bound by stating that the ratio is alpha Tx over T is at least that alpha mx plus n minus 1 over m plus n minus 1. Now, here we can easily see if we plug in m equals to 1, we will get back the Junoskis bound. Now, I'm going to introduce or then describe the Zariski-Nagata theorem, which is going to give us an algebraic platform to study that geometric property or the geometric problem. To introduce to Zariski-Nagata's theorem, first I need to introduce two objects. I think this is really well known and popular in these days. One is symbolic powers of an ideal, and second one is the differential power. Now, given an ideal, the symbolic power is defined as by extending the ordinary power of the ideal to the pth localization, then contracting it back to the ring, and then taking all those intersections with respect to the associated primes of the ideal. Now, the differential power, as it sounds, it uses the differentials, and when you take an element inside the ring and you take the differential of order up to t, you will get back an element inside the original ideal. And delta here, I denote the, I use the symbol delta to denote the partials. Zariski-Nagata theorem for a perfect field and a radical ideal, it gives us the, it tells us that the symbolic power and the ordinary power of an ideal is going to be, just a minute. I do. Oh, okay. Can you see my screen? Okay, yeah, sorry. So, yeah. So the Zariski-Nagata theorem tells us that the symbolic power and the differential power of the radical ideal inside the polynomial ring is always same. And one more thing to talk about in the powers, that the symbolic power and the differential power, both of these powers are defined for more general setup, but for the perspective of my talk and since all of the work are in polynomial rings, I am just going to stick to the definition here only, which is applicable for the polynomial rings. Now for fat points, in Pn, Zariski-Nagata theorem also tells us something more interesting. It tells us that the mth symbolic power of the defining ideal of the points x has a really nice form, which is given by, if we have the points p1 up to ps and small scripted pi is the ideal defining the point pi, then we take all those small mth ordinary power of all those prime ideals, then we intersect all those ideals corresponding to the points, then we get the symbolic power of the ideal defining points. So we no longer need to use this or look into this definition of the symbolic powers. We can just think about all the prime ideals corresponding to each point, then taking their ordinary power and intersecting them. And this set is same as the set we wanted to study. It is the set of all homogeneous polynomials that will vanish on the set X with multiplicity at least m. And similarly, for fat points where the points are going to have multiplicity m1 up to ms respectively, that ideal is defined by taking the prime ideal corresponding to each point, taking the ordinary power of the corresponding multiplicity and intersecting each of those components. And this ideal is the same set as we wanted to give our motivation from, is the set LXMI. Now, Zariski-Nagata theorem also gives us more. It tells us that alpha tx that we want to study is basically the initial degree of the teeth symbolic power of the defining ideal x. Again, with a little computation, we can prove that the h symbolic power and the b symbolic power, if we take the product of those two symbolic powers, the whole product will lie inside the a plus b symbolic power of I. And by taking the initial degree, we can say that this initial degree will satisfy subadditivity for any ideal I. Now, since this is subadditive, by Feket's lemma, we know the ratio of the initial degree of the teeth symbolic power with t has the limit, and which is same as the infimum of the ratio. And this number is denoted by alpha hat, and sometimes it is also denoted by gamma, and it is known as to be the Waldschmidt constant of the ideal I. Now we have defined the Waldschmidt constant, then we will be seeing some equivalent statement for the conjectures. First of all, the Nagata's conjecture, if we take a set of general points in P2 and Ix be the defining ideal, then the ratio of the initial degree of the teeth symbolic power with t is at least the square root of s, and which is similar to saying that the Waldschmidt constant of the defining ideal is at least square root of s. Now, in the similar fashion, Junoskis conjecture and de Mailly's conjecture has that equivalent format where we get that the Waldschmidt constant of the defining ideal of x for Junoski has the lower bound, which is the initial degree of the defining ideal plus n minus 1 over n. And for the de Mailly's conjecture, the Waldschmidt constant of the defining ideal x has the lower bound as the initial degree of the mth symbolic power plus n minus 1 over m plus n minus 1. Now we have the equivalent statements. What we will be doing next we will be seeing the known results. So Junoski's conjecture and both de Mailly's conjecture, there are many known results. I'm going to explain the results. So Junoski himself proved the result for P2, and also Harbourne Huneke proved the result for P2. And Harbourne Huneke used some kind of containment, to prove the actual bound. Now, Dubinsky proved the Junoski's conjecture for general points in P3 and points at most n plus 1 general points in P and K. Excuse me. So Bokchi and Harbourne proved that Junoski's conjecture is true for binomial number of points in P and K forming a star configuration. Later on, Dubinsky and Tutas-Gazinska, they proved that the Junoski's conjecture is true for at least 2 to the power n many very, very general set of points in the projective space. And Pauli, Montero, Z, they proved that Junoskis conjecture is true for very general points in P and K. Now, Duminsky and Tutas-Gazinska, they used the technique of containment, and they proved the containment holds for those many points. And Pauli, Montero, Z, they use some kind of geometric approach and use the specialization in there. Now, in the recent work with Grifo, Ha, and Nguyen, so what we proved the Chudnovsky's conjecture for at least 4 power n many general points. Now, similarly, Dimilis conjecture is also known for many cases. And the first thing I want to mention that this n should be 2. Otherwise, there is no point of proving, working on this project. So Esnold and Vivek proved the Dimilis conjecture for P2. Later on, Malara, Somberg, and Spons, they proved Dimilis conjecture for S many very general points, and the number of S many points that satisfies this condition where we have to take the floor function of nth, a floor function of the 1 by nth power of S has to be at least n plus 1, which was extended by Chong and Zhou, and they showed that the Dimilis conjecture is true for S many very general points where S satisfies this little bit stronger inequality. So in our recent work with Eloisa, Taiha, and Thai Nguyen, we proved that Dimilis conjecture holds true for at least 2m plus 2 whole power n many general points in P and C. Now, I have said this word like general and very general so too many times. I'm going to give an introduction and define somehow what I meant by general and very general points. So whenever I have some points in the projective space, suppose P1 up to PS, then I can write down their coordinates as follows, like A10, A11 up to A1n. Similarly for PS, AS0, AS1 up to ASN. This tells me X is associated to the following matrix, which we can think as an element inside the affine space with dimension S times n plus 1. Now, what the idea of general and very general comes with an open set inside this affine space. And what we did, we tried to make these coordinates generic, meaning we see these coordinates as generic coordinates, and we constructed for each row we use those as points, and we constructed the generic points. I mean, if I say if this idea was introduced in the Fowley Montrosi's paper. So what is done there? What is done is, so take Z to be Zij, S times n plus 1 many new indeterminates. Then we take the transcendental extension of the field K, and then, as I said before, this for each row, that row corresponds to the point which is denoted by PIZ, but this time these points, they sits inside the bigger projective space, which is PNKZ. Now the dimension remains same, but just the field becomes somehow becomes larger than the original field. So this set of points XZ with P1Z up to PSZ is referred to as generic points, generic S points in the projective space, PNKZ. Now, when we have this generic point, if I go back to the previous slide, somehow these Zijs can be replaced with those points, Aijs, and we can get back points inside our projective space. So that's the idea. We so consider an element inside the affine space. Now by replacing Z with A, we can find an open set such that when we replace each point of that open set inside that generic points, we will get a set of distinct points in Pn for all A inside that open set. Now, having said that, Fowley-Montarzi, they proved that a property P is said to hold for very general set of points if there exists an infinite intersection of open sets W, and that every of these open sets sits inside the affine space with dimension s times n plus 1, such that the property P holds for xa whenever A inside the intersection. Now, a property P is said to hold for a general set of points if there exists an open set inside the same dimensional affine space such that that property is going to be satisfied every time we will do the replacement with Z and A. So very general means something is going to satisfy for points inside an infinite intersection of open sets, and general means it is going to satisfy for an open set. And this intersection of open sets is an infinite intersection. So in general, we cannot say that it is an open set. We have to produce some different way. We have to use some different technique to produce that exact open set for which some property is satisfied. Okay. Now our idea, our approach to tackle the problem was the approach via containment. Containment illustrates when some symbolic power of an ideal will be inside some ordinary power of the same ideal. Now, the first theorem that is stated here is really interesting result, which was proved by in different works in Lazarfield Smith, Oxter Huneke, and Ma Schwed. And they proved that if we take a radical ideal with big height h inside a regular ring, then the HR symbolic power of the ideal sits inside the earth ordinary power of the ideal. And that happens for every R inside the naturals. Now, if we do a little bit of computation, this will tell us, this will infer that the Waldschmidt constant of the ideal is at least alpha I over H. So can this bound be improved? Can this bound of the containment be improved? So the answer is of course yes, as we can see Harbourne conjecture that if we take a radical ideal with big height h inside the regular ring, then the HR minus h plus 1th symbolic power sits inside IR. And with that conjecture, Harbourne and Huneke strengthen that conjecture by including appropriate power of the maximal ideals on the right hand side. By that I mean, if you let R be the coordinate ring of the projective space, meaning the polynomial ring with n plus 1 variables, and I is an homogeneous radical ideal with big height h, and M denotes the maximal ideal, then Harbourne Huneke conjectured that number 1, the HR symbolic power sits inside M ordinary power RH minus 1 times ideal product with I ordinary power R. They also conjectured that the R times M plus H minus 1 symbolic power of I also sits inside R times H minus 1 ordinary power of M times M symbolic power of I whole ordinary power of R. Now again, if we put M equals to 1 in the second containment, then we will get back the first containment conjecture. So right now, I would like to uh, say again that our focus is to study these containments for ideal defining points in P and K. And when I am talking about ideal defining points, then the big height H becomes N. So one of the reasons that these containment conjectures are interesting is that those containment conjectures gives us Junoskis conjecture and the de Mailly's conjecture. So for a uh, quick proof of that, if we take I to be an ideal defining set of points in the projective space, and it satisfies the Harbourne-Huneke containment, which is n earth symbolic power sits inside Rn minus 1 ordinary power of m times IR. Then if we take the initial degree in both sides, we will be getting that initial degree of the nth symbolic power is at least r times alpha I plus n minus 1. Then if we divide by nr in each side and take the limit as r goes to infinity, we will get back the statement of the Junoskis conjecture, meaning the Waldschmidt constant that alpha hat I is at least the alpha I, the initial degree of I, plus n minus 1 over n. In a similar fashion, if we take that other containment of the Harbourne-Huneke and do the same way, take the initial degree, divide each sides by proper power and take the limit, we'll get de Mailly's conjecture from this containment. So that is one of the one of the interesting reasons to study those containments. I mean, uh, to study the containments they do have their own beauty to study, but that is one of the ways to look into their importance. Now, do the containment conjectures always hold? The answer is no. There exist counterexamples to Harbourne's conjecture, and it was by Dubinsky, Schomburg, and Tutas Gazinska, and also by Harbourne and Siciliano. But this this counterexample is really interesting, but we have to see, we have a scenario where we can take the limit. So we can avoid what happens for first few cases. We just need to look into what happens after some stage and from there onwards. So what we study the stable containment, meaning we study the same containments, but we study those containments for R big enough. Now, the stable containment R as it is the coordinate ring of the projective space, and I is the homogeneous radical ideal with big height H, and M is the maximal ideal. Then the stable Harbourne conjecture, which is stated as same containment, but now it is stated for all R big enough. And the stable Harbourne-Huneke containment, and has the same format, but instead of having for all R, now it is for all R big enough. And again, for the other Harbourne-Huneke containment, here we are interested to see this containment for a specific configuration of R, which is given by R equals to Ct for some fixed C and for all T inside N. And I would like to call this as a weaker stable Harbourne-Huneke, because it is not actually as strong as all as strong as the previous ones. Now I put the statement 3 in that particular format because then one reason was that particular format was helpful for us to get the de Mailly's bound. Of course, one expects to study this number 3 for all are big enough, but for our case we had to focus on only this particular configuration and to get that de Mailly's bound. Oh, one more thing I need to mention here, that the stable Harbourne statement, it was first introduced by Eloisa in her work that I forgot to mention here. And yeah, and that was all the reasons that we are interested in the stable containment with proper maximal ideals and a little bit of weaker stable Harbourne Huneke containment. Now, the results about the containment and the stable containment. So Stefan Tohanianu and UC proved that the stable Harbourne containment is true, meaning this containment I symbolic power nr minus n plus 1 sits inside IR. This holds for a very general set of points in the projective space. Now Harbourne and Huneke proved that the first Harbourne Huneke containment, meaning the nth symbolic power, sits inside I earth ordinary power times mth ordinary power with Rn minus 1. This holds for ideals defining any general points in the projective plane. Later on, Duminsky and Tutas-Gazinska, they proved that the Harbourne Huneke containment, meaning the containment with I symbolic power nr sits inside IR, I ordinary power R, and M ordinary power Rn minus 1, that holds for ideals defining at least 2 to the power n many very general points. And the last Harbourne Huneke containment for the last one that I stated was partially proved by Bokchi, Susan Cooper, and Brian Harbourne, and they proved for cases where they took the points to be a square many points, a square many general points, and the points were coming from the projective plane. Now, in our recent work with Eloisa, Taiha, and Thai, we proved that the stable Harbourne containment holds for ideal defining any general set of points in the projective space. Secondly, the stable Harbourne Huneke containment, meaning the containment states the nth symbolic power of I sits inside the R times n minus 1 ordinary power with I ordinary power R. This containment holds for at least 4 power n many general points in the projective space. And lastly, the Harbourne Huneke containment I symbolic power Rm plus n minus 1 sits inside M ordinary power Rn minus 1 with mth symbolic power of I whole power R. This containment is true for that special configuration where R is given by Ct for some C which is fixed and for all T in N. And this containment is true for at least twice m plus 2 power n many general points in the projective space. Now I'm going to introduce one of the important techniques that has been used, and this is specialization. So specialization, the way I think it as a evolved evaluation map that takes an ideal inside the bigger ring, which is in our case KZX, and gives us an ideal which sits inside the coordinate ring KX. And how does this specialization map work? So we pick up the ideal from the bigger ring, then we look into all those elements which doesn't have any denominator in terms of Z. So they look like this, I intersection with the polynomial ring KZX. Then we evaluate the element A at those values for the Zth coordinate. And thus the specialization map pi A is going to that gives an ideal inside the coordinate ring Kx. And once again, the X is all X here is the all the coordinates x0 up to xn, and Z denotes the coordinate Zij. Now the specialization does have many interesting properties. I'm going to give a really nice example, which is nice to start a basic example and also nice to see that specialization, it is not always like what we can think of. Like to get a specialization of the ideal, you cannot just specialize at the generators. So the ideal is given by xy, which is same as x comma x plus uy inside the polynomial ring with ku xy. Now, if we want to specialize at 0, then the ideal becomes xy. But if we specialize at these generators x comma x plus uy, we will not get the exact ideal that we want to get. So whatever I said is a theorem that was by Krull, and it says that if we have a set of generators, which is given by F1 up to Fl, then there exists an open set for which only open set for which the specialization of the ideal is the specialization of each generator. Now, in the previous example, as we have seen, that specialization, that open set is going to be proper because for this ideal, 0 doesn't belong to the open set where you can just specialize the generators and you will get the ideal back. And the next theorem, it says that if we take two ideals, I and j inside the bigger ring, then specialization at the intersection of the specialization is the specialization of the intersection, but that happens only on an open set. Similarly, specialization of the product is going to be the product of the specialization, but again that will happen on an open set. Now, a natural question is that open set proper? I mean, the answer to that is, as you can guess, yes. And with examples, it's easy to see that if we take the ideal, that principal ideal generated by x1 and other one x1 plus gx2, then the specialization of the intersection is going to be x1 squared, which sits properly inside the specialization of the individual, which sits in which sits properly inside the intersection of individual specialization. Similarly, if we take an ideal which is generated by x1 comma x2 plus zx3 and z to be x1 x2, then the product of the specialization sits properly inside the specialization of the product. So for each of these scenarios, we will get a proper open sets. Now, why we are studying this open set and why the specialization, the missing link is given here. So if we suppose PIZ to be the ideal for the generic point, and PIA, scripted PIA, is the ideal of the point capital PIA inside the projective, the smaller projective plane, then there exists an open-end subset such that if we specialize the prime ideal corresponding to the generic points, we will get the prime ideal corresponding to the normal point. And it tells us more, and it tells us that if we are taking the symbolic power or the ordinary power of those ideals, then there exist open sets, and the open sets depends on the power each time, such that the specialization of the symbolic power is going to be the symbolic power of the coordinate wise replacement. Same specialization of the symbolic power of the ordinary power will be ordinary power of the coordinate wise replacement. Now, this helps us to gain open sets, and again we want to get open sets where these containments are true. Now, now uh, I'm going to state how the result in general, how the result about the very general points have been proved. So the idea is to prove the containment or the inequality for generic set of points, as it is here that the ratio of the generic set of point is at least the ratio alpha ixc plus n minus 1 over n. Then for each of these m, there would be an open set where the the points will satisfy the inequality. Now, when we have the open set, we will be taking the intersection of all these open sets. Then the result about the uh, lower bound of Junoskis for very general points will be satisfied, meaning we will take for each m, we will be getting an open set. I mean, yeah, they got an open set for each m, then they took the intersection. After they took the intersection, they got the result for the Junoskis for very general set of points. Now, we had to somehow come up with an idea where we have to avoid taking the infinite intersection. There comes the result of Eloisa, which expresses taking one containment is enough to get the stable containment. Meaning, if if for an ideal that one particular containment is satisfied for some C, then for all are big enough, one can prove that the stable containment is true, and we proved uh, in the same spirit, in the joint work with Eloisa, Taiha, and Thai, we proved that if we take a radical ideal with big height h, and suppose for some integer c, this containment is true, but now this time we have an appropriate component with the maximal ideals, then we could prove that this stable containment is true. In the similar fashion, we could generalize a little bit more what we could prove if for some constant c, if this particular containment is true, then for all t in natural numbers, we can prove this stable, somehow weaker stable version is also true. These two theorems helped us to get rid of the intersection of open sets, and we could get the results by taking just one open set. So these theorems does have really interesting application. The first one I would like to explain is the Fermat points with n square plus 3 points. Now the ideal is defined by x y power n minus zn, y z power n minus xn, and similarly with c component. Now, if we assume the characteristic has to be not equal to 2, then these ideals fail to satisfy the Harbourne conjecture, meaning it failed to satisfy the third symbolic power sits inside the second normal power or second ordinary power. And it was proved by Harbourne Siciliano, also by Dubinsky, Sombor, Tutas, Gazinska. But for these ideals, we could prove that the 10th symbolic power sits inside the 6th ordinary power of m and 6th ordinary power of I, which means I26 minus 2 sits inside m6 I6. Now, once we could prove that, and now we can use our previous theorem to say that this containment is true for all are big enough. Now, once this is true, then it is easy to say that these Harbourne-Huneke containments are also true. Now, the second example I would like to explain is the example from Borowski configuration. In the same manner, we could prove that the 8th ordinary, So before I explain the result, so this is a configuration where 12 line meets in 19 triple points. And for these ideals, we could prove that 8th symbolic power sits inside M7 and I5. So again, using our previous theorem, we could prove for these ideals too that the I symbolic power TR minus 2 sits inside MR and IR for all R big enough. And basically this containment gives us these two containments. Now, the big application of our theorem, one containment implies stable containment, is the Harbourne-Huneke containment for general points. So if we suppose the characteristics of the field to be 0 and n is at least 3, and I defines the ideal for general set of S points where S is at least 4 power n, then the stable containment I symbolic power nr sits inside mrn minus 1 and I power r that holds for all r big enough. Now, as I have stated this before, that theorem 2.13 implies the Junoskis conjecture for at least 4 power n many general points. Now, for the de Mailly, the idea is same. So if we have n to be at least 3 and k is twice m plus 2, and S satisfies this condition, meaning S is at least twice m plus 2 whole power n, then for those ideals, we could prove this containment is true. Now, once we prove this containment is true, then the consequence of the consequence says us with the same setup as before, for these many general points, we could prove the de Mailly's conjecture de Mailly's conjecture is satisfies for those many general points. Now, I would like to give a brief outline of Junoskis conjecture, how we proved. First, we took the generic points, then we proved one containment for the generic points. Since C is fixed, we get an open set where we can specialize. And for that particular open set, we will get this containment is true. Now we know that one containment will imply the stable containment. So from here, we can get the appropriate stable containment for all those points inside the open set. And once we get all those points, once we get that stable containment for all those points inside the open set, then from there, we can prove that the Waldschmidt constant for all those ideals defining those points is going to be at least the initial degree of the ideal plus n minus 1 over n, meaning we will get the Junoskis conjecture. Secondly, it's for the de Mailly, it's the same idea, but little bit weaker, because proving that containment depends, proving that one containment for generic points is really difficult, and we had to assume the number of points is going to be depending on m. And once we prove that one containment, again the same trick, there exists an open set where we can take the specialization. Now once we take the specialization, we have that one containment, and this one containment will imply the containment that gives us the de Mailly's conjecture. So once we have this particular containment for general set of points, we can derive that the de Mailly's conjecture is true for all those general set of points. Now, lastly, I will like to talk a little bit about some ideals which are different than the points. Now, so far, all the results that I have talked about, mostly they cluster around the ideals defining points. Now, this one is about the star configuration of codimension H. So what how it is defined? It is defined as we take n many hypersurfaces so that they intersect properly. Then for each h, which is at most n, we take the intersection of all those h many hypersurfaces, and we take all the possible unions that can be formed like that way. We call this VH is the codimension H star configuration. Now, if all these hypersurfaces H1 up to Hn is defined by the forms, which is F1 up to Fs, then the ideal is defined by the intersection of all these H pair of forms Fi1 up to Fih and taking the intersection. So for these kind of ideals, for these ideals of star configurations, we could also prove the containment, which also implies the de Mailly-like bound for those ideals. And lastly, the determinant rings. So these rings are really, and determinant rings and ideals, these ideals are really well known. And it is defined as if we fix a T which is minimum, which is at most the mean of P and Q, where P and Q is the dimension of a matrix, of a generic matrix of indeterminates, and we consider the polynomial ring coming using those indeterminates, then the ideal that that is the ideal of T by T minus of X, it is proved that the height of those ideals is given by product of T minus P minus T plus 1 times Q minus T plus 1. Now, we proved in the joint work with Eloisa, Taiha, and Thai that those ideals satisfies the Harbourne-Huneke containment, meaning the R times H plus M minus 1 symbolic power sits inside H minus 1 times Rth ordinary power of the maximal ideal with the product of mth symbolic power with the R ordinary power. Now for these kind of ideals, since they satisfy this containment, we say that these ideals also satisfy the de Mailly-like bound, meaning the Waldschmidt constant is at least the initial degree of the mth symbolic power plus h minus 1 over m plus h minus 1. Now, I would like to talk about a little bit of where I want to go from these projects. Now, our results, they are for large number of points. I'm interested to look into different methods that will give us something about smaller number of points. Now, the containment results are mainly for points, and there are some cases where we prove the containment for different ideas. So I'm interested in the ideals that are coming from different setup, different like combinatorial or different arrangements. I am interested in that. Our de Mailly's conjecture does depend, our result about the de Mailly does depend on the bound, on the number m. I would like to investigate more to see how can I get rid of that m. Lastly, I'm interested in to see the Hilbert function of the fat point scheme. Now, the well-known SIGH conjecture that predicts the maximality of the Hilbert function. So I'm interested to study that that conjecture also. And thank you for listening.
All right, let's thank Sankhaneel. Questions? Sankhaneel, would you mind going back 2 slides to the determinantal? My brain must be broken. The symbolic powers of those ideals aren't just the regular powers? Okay. Broken. Thank you.
To take maximal minors, they are. Otherwise, they're not.
Thank you. Thank you. Other questions, more educated questions?
I actually remember one question. I mean, you kind of half answered my questions at the end of the talk, but can you go back to when you were talking about star configurations? Okay, so the bound you obtain down there, that's not the staple container, right? Containment. It's a
No.
little different.
Yeah, it actually this holds for every m and c. So it's like a, so what we could prove that the ideal, they satisfies the original Harbourne-Huneke containment without any assumptions or on C or M. So we could prove something stronger than that, and that's the statement here. So we don't, for this ideal, we don't need to assume that it is going to happen after some stage or some R big enough.
Okay, cool.
So it's like that containment on steroids, right? It's even better.
Nice.
Other questions?
Actually, I have a follow-up. Do you know if this is the best possible containment, or?
So what I was when we were working, so we were hoping for this to happen. So if I can say, for suppose I is the ideal, so we were hoping something stronger like this happen, but we could not prove it. So it is little stronger than the Harbourne-Huneke. Like we have -n+1. We were hoping to prove that, but there were some calculations. We thought actually we proved that, but while revising, it came out wrong with -n+1.
Okay, thanks.
Other questions? All right, let's thank Sankhaneel for the nice talk.